I have a very interesting question for you. In the previous lecture, when we were discussing zero biasing, like in the circuit as shown, then what will be the potential difference between the two ends of the wire? Will it be zero? Or will it be equal to the contact potential V0? If it is zero, then where does the potential drop across the depletion width go? The answer is zero. The potential drop across the two ends of an ideal wire will be zero, and you have to understand why is it so. At first, you should understand that the majority carriers from the p-type and the n-type region moved across the boundary, making a depletion region because they were in contact. But the wire is also making a contact, meaning that majority carriers will flow through the wire, creating another region at the boundary of the semiconductor crystal, which is depleted of charge carriers. The formation of another temporary depletion layer compensates the built-in potential such that Kirchhoff's voltage law across the circuit is satisfied, and this is why the potential drop across the two ends of the wire is zero. And this is the same reason why we cannot measure the built-in potential through voltmeter. Remember that we have taken a practical diode and ideal wire. You may not be solving much questions relating to ideal diode in electronic devices and circuits, but in analog electronics, you may have to solve certain questions which are based on ideal diode. In later lectures, we will see what are the differences between practical and ideal diode. Now, we talk about the parameters which are affected by biasing, particularly by forward biasing and reverse biasing, as the parameters will remain same in zero biasing. We have formula for depletion width, which is given by now for forward biasing, this formula will modify to. Similarly, the formula for reverse biasing will be modified to. And the formula which we have is of maximum electric field, which is given by. This expression can actually be written as minus 2V0 divided by depletion width. This formula I have already derived, and this is just a rearrangement. If we first put the value of Xp in terms of doping concentration and acceptor concentration, and after rearranging the equation in terms of depletion width, you will get this expression. It is actually quite easy to remember this formula because you know that electric field is actually equal to negative of potential gradient. So we can remember by using this analogy, like Emax is equal to negative, potential you know, the potential drop is V0, the total distance x is depletion width. Now you have to simply add an extra 2 which will give you the formula. Remember that this is just an analogy for remembering the formula for step graded junction. Don't take it too seriously, as it may not be valid for other types of concentration profiles. Anyways, the maximum electric field for forward biasing will come out. Similarly, for reverse biasing, formula will modify to. There is actually no need to learn formulas separately. You can unite the formulas by fixing the direction of the battery. Let's assume that we have a diode which is connected to a battery. Now, since the direction is kept in forward biased, then maximum electric field will be. Similarly, depletion width will be. If the applied potential is positive, then it will automatically be looking like the forward bias formula. If the applied voltage is negative, then in the final expression, it will cancel the negative sign such that the final formula will be similar to the reverse bias formula. We can simply say applied forward bias is actually equal to negative of reverse bias voltage. By observing the formulas, you can see that after applying an external voltage, you have to simply modify the voltage term in the expression of these formulas. Otherwise, the formulas remain the same.